I welcome all of you to Pune College of Arts, Science and Commerce College, Camp Pune 1. Myself, I am Dr. M.B. Pathan. I teach Statistics Paper 2, Discrete Probability and Discrete Probability Distribution. Last lecture, we have studied different problems related to classical probability. Today we are going to study limitations of classical probability and then we'll proceed ahead. Limitations of classical probability. The classical probability is not used to get answer of the following questions. Question number 1. What is the probability that a student will pass an examination? Question number 2. What is the chance of celebrating next birthday for a person? Why classical definition is not applicable for such type of question? That we'll try to study. Suppose I try to solve question number 1. What is the probability that a student will pass an examination? If I try to apply classical approach, every student has two possibilities. He or she will pass exam or fail exam. That means for every student there are two outcomes. We are trying to get probability to pass exam. So favorable outcome is 1, total outcomes are 2. So classical approach says chance of pass an examination is 1/2 and chance to fail an examination is 1/2. That means it says 50% chance is to pass examination and 50% chance to fail examination. That means if I want to interpret this calculation in general, suppose there are 70 students in a class. So this calculation says 35 students always pass exam and 35 students always fail exam, which is not true in the real life. That means for solving such question through classical approach gives wrong answer, misleading answer. Now why we get wrong answer? Why we get misleading answer? That reason will be obtained by studying a classical definition. If you recall the definition, what I had given you, it works like this. Let the random experiment have n mutually exclusive and equally likely outcomes. That means if you want to apply classical probability in the real life, you have to check the outcome of experiments are disjoint and they should be equally likely. This condition does not satisfy by this question. For every student to pass exam and to fail exam are not equally likely. It varies from one student to another student. Some students have good IQ in mathematics, so he will have more chance to pass exam related with calculations. Some students have good IQ in literature rather than mathematical oriented topics. So such students have more possibility to pass exam in a theoretical oriented, in literature oriented. So for this question, the condition of equally likely outcome does not satisfy. And that is the basic reason why you are not able to apply classical approach for this question. If you apply, your answers will be wrong, answer will be misleading. Similarly, you have second question. What is the chance of celebrating next birthday for a person? Again, in this question, we have two possibilities. Person can celebrate birthday or person cannot celebrate birthday. Now, celebration of birthday and non-celebration of birthday are not equally likely. If I apply the classical approach, I will get again 50% chance to pass, so to celebrate, and 50% chance to non-celebrate, which is not happening in the real life, because celebration of a birthday depend on the age of person. If person under study is 40 to 45, 40 to 50-year-old, he has a more chance to celebrate coming birthday. If I took another person, suppose 80 to 90-year-old, so celebration of next birthday for a person who belong to 80 to 90, chance of non-celebration become more. And that is why in this example also, outcomes are not equally likely. And that is the basic reason why classical approach not applicable for such type of questions. So what this discussion tells you, it says that your classical approach has certain limitations. And that limitation is outcome of experiment should be equally likely. If outcomes are not equally likely, you cannot go by classical approach. You have another limitation. Sometimes outcome of the random experiments are infinite. That means n equal to infinity. Even though experiment provide equally likely outcomes, but they are infinite. So classical definition says probability equal m divided by small n. If denominator is infinity, then every time probability becomes 0. So this is the second limitation where you cannot go by classical definition. You have example for this where you get n equal to infinity. Tossing of a fair coin, coin is fair. That means outcomes are equally likely. But I repeat the experiment till to get head. So for such type of experiment, your sample space is like this: H, comma TH, comma TTH. I told this when I taught sample space and event. So this is the infinite collection. And therefore, n become infinity and your classical definition become unapplicable. So we have following limitations for classical approach. Number one, outcomes of random experiment should be mutually exclusive and equally likely. These both conditions should be satisfied. Then you can apply classical approach. And second condition is total outcome of random experiment must be finite. Then you can go by classical definition of probability. So naturally one question arises in mind: if you are not able to apply classical approach, Then how to solve such type of question in the real life? How to get answer of this? How to get answer of this? And for this reason, we have another approach to calculate probability that is called as probability model. It is also known as probability assignment approach. So we'll try to study the second approach to probability under the heading probability model. So this is topic number 2. You also known as probability assignment approach. Let us see how to define it. Let omega equal curly bracket omega 1, omega 2 up to omega n. We have a random experiment which has finite outcome. Suppose on this omega, I define a function as p. Be a model defined on each sample point wi of omega such that, excuse me, hello, Wolfram, what happened? गूगल मीट का लिंक लगाया क्या आपने? Now try again.
Thank you, sir.
Okay. So we'll try to define probability model. We have a sample space with n elements. On this sample space, I define a function p such that p define on each element which is greater than equal to 0 for every element I1 to n. And second condition, total of the function equal to 1. So any model which satisfies these two conditions is called as a probability model. So for W1, I assign one value which is positive. For W2, I assign another value which should be positive, and so on. And second condition, when I make addition of all these values, the total should be 1. Then such function, such model is called as a probability model. That other word is probability assignment approach. Such model P is known as probability model. So you have to remember two conditions. Under probability model, every value should be non-negative and total of the values should be 1. Let us try to see simple example based on probability model. Verify whether following models are probability model or not. I put 3 different bits, 3 different questions, sub-questions. Number 1, PW1 is 0.2, P of W2 is 0.3, P of W3 is 0.18. P of W4 is 0.32. Second sub question, PWI is I by 4. I takes value 1 to 4. Third model, P of W1 is 0.25. P of W2 is 0.35. P of W2 equal to 0.45. P of W4 is minus 0.05. This is assignment by the given person. You want to study this assignment represent probability model or not. So how you can verify? You can verify with the help of these two conditions. Your model, your assignment represent a probability model if probability of Wi greater than equal to 0. Sum of probability equal to 1. Let us consider first question. Each number is positive. So my first condition trivially true. This is for all I, not plus, for all. Summation PWI, I from 1 to 4. I want to verify now second condition. So this is nothing but PW1 plus PW2 plus PW3 plus PW4. Put the values what is given in the question. If you make an addition, it comes 1. Every number is positive, total is 1. So answer is given model is probability model. Similarly, you can speak for second question. PWI, I by 4. I takes value 1, 2, 3, 4, 4 outcomes. I can write separately PW1, 1 by 4. PW2, that is 2 by 4. PW3, 3 by 4. PW4, 4 by 4. Every value greater than 0. First condition satisfied. What about the second condition? Make the total of all these probabilities. 1 by 4 plus 2 by 4 plus 3 by 4 plus 4 by 4. 4 is common LCM. So you get answer 10 by 4. And 10 by 4 is 2.5, which is not equal to 1. So second is not a probability model. Let us think about number 3. What you can say for this now? You can check each value. Are they positive? Answer is not. This number is minus. This number is minus, which is not allowed in probability model. That is why number 3 and number 2 does not represent probability model. They represent only one is probability model, second and third is not probability model. Now we proceed another question related with probability model. A loaded die has following probability assignment to the outcome of experiment. What is experiment? You have a die, you are throwing it. We know dice has 6 possible outcomes. So that die is loaded, which is not biased, unbiased, it is biased. So chance of getting 1 is 0.1, chance of getting 2 is 0.2, and so on. What is the probability of getting an even number on the upper face? What is the probability of getting number less than 4 on the upper face? We have seen such example under classical probability. But there I say a fair die, unbiased die. So we take 1 by 6 as a probability for every outcome. So under this assignment, I want to solve this question. So let us define event as below. A, getting an even number. So probability of A is sum of probability of Wi. I am interested in even number.
Sir, is
So
this
it's
example
going
in textbook?
Yeah.
Is this
Hello?
example is in textbook?
I think it may be or may not be. Okay.
Okay, sir.
Even number, that means my outcomes are 2, 4, 6. So chance of getting 2 plus chance of getting 4 plus chance of getting 6. Now this is given in the question. Put the values of probability and make a total. So there is a 50% chance to get even number in your experiment. What is the second bit? Number less than 4 occurs on the uppermost. So B equal event B, a number less than 4 occur. So B equal 1, 2, 3, less than 4. So chance of getting B, it is not A, it is B. Probability B equal P1 plus P2 plus P3. Add these probabilities, there is a 60% chance to get such event. Let us go for one other example. 3 girls and 4 boys take part in an Antakshari competition. 7 students, out of 7, 3 are girls, 4 are boys. They are playing Antakshari. Those of same sex have equal probabilities of winning. But each girl has twice, the spelling is wrong, twice, as likely, double, twice means double, as likely to win as boy. So this is the condition. This is the past experience. Find the probability that a boy wins the competition. Let us see now what the question says. We have 7 students. Out of 7, 3 are girls, 4 are boys. Chance for the same sex equal, and chance of girls over the boys is double. This is your information. Now, by using such information, you want to get answer of the question. Solution: let B indicate boys, Z indicate girls. So we have sample space Z1, Z2, Z3, B1, B2, B3, B4. 4 boys, 3 girls.
Let 3 boys and 4 girls.
Yeah, 3 girls, 4 boys. So omega has 3 girls and 4 boys. Is it okay? In the question,
Okay,
3 girls are there and 4 boys are there. So number of participants are 7. Understand? Let
Yes, sir.
P equal probability of winning competition by boys. So probability of winning competition by girls will be 2p, because question says girls has double chance than boys. If p is the probability of winning by boy, then 2 times p will be probability of winning by girl. Now what is p? That is not given. It is assumed by us. So we find unknown constant p under probability such that probability of omega always 1, because probability of complete sample space always coming 1. So what is p omega? It is probability b1 plus probability b2 plus probability b3 plus probability b4 plus probability z1, z2, z3. Total is 1. This is assumed to be p. So we write p plus p plus p plus p for 4 boys, plus 2p, 2p, 2p. 2 is common, so p plus 3 plus 3. So this is 10 times p equal to 1. So p coming 0.1. So what is this p? It is the chance to win the competition by boy. So what is the chance for girl? It is 2 multiply 0.1, 0.2. That is double. Now what is the question asked? Question asked, we want to find probability of event boy wins the competition. So chance of winning the competition by boy, it may be any one boy, not specified. So p of b1 plus p of b2 plus p of b3 plus p of b4. That is 4 times p. So it becomes 0.4. Hence, probability of winning competition of girl will be 0.6, because for one girl chance is 0.2. So competition may be won by any one girl, maybe z1, z2, z3. So 0.2 plus 0.2 plus 0.2, that is 0.6. So this is the example which is related with probability model. Now we go for third approach of studying a probability, that is axiomatic approach to probability, which is also called as modern approach to probability. We have some statements related with probability. Before going to ahead, I will try to explain what is the meaning of axiom. Axioms are a statement which are true by itself. Any statement which is true by itself is treated as an axiom. What is a theorem? Theorem is statement which requires the proof. That is called as a theorem. That is the basic difference between theorem and axiom. If I want to explain this with some illustration, I will say the sun in the sky. When I make a such statement, the sun in the sky, everybody will accept it. So such statements are treated as axiom. Whereas if I say the shape of earth is spherical, is round. Now even though we are a student of science, are we ready to accept this as it is? Answer is not. We require some evidence. So statement number 2 the shape of earth is round. It is proved now. But the person who is a layman, which is not educated, he will say how? So second statement required support, required proof. So I will say second statement is a theorem and number one statement as the axiom. The sun in the sky, the moon in the sky. Nobody will take objection. Self-true statement are axiom. So related to probability, we put three statements. Those are taken as self-true. Number one, if A is any event of omega, then probability of A always greater than equal to 0. This is axiom 1. Axiom number 2, if omega is a sample space of a random experiment, then P of omega always 1. Second axiom. And axiom number 3, if capital A and capital B are two mutually exclusive, you can call disjoint events of omega, then probability of union will be P of A plus P of B. So these are the three axioms which are true for probability. By using three axioms, we will try to develop some theorems and we'll make the proof of that theorem by picking these three axioms. So any probability obtained with the help of these three axioms called as axiomatic approach to probability. Other word is modern approach to probability. So by including this, it is a third one. First approach, classical definition. Second approach, assignment, probability assignment approach called as probability model. And third is modern approach called as axiomatic approach to probability. So these are the three approaches to study probability. Let us see some theorems on probability. The following are theorems on probability which can be proved by using axioms and with the help of Venn diagram. Theorem number 1. If A is any non-empty event of omega, then P of A dash is 1 minus PA. Other way around, it is PA plus PA dash equal to 1. Let us recall remark which I had given you under classical definition. In that remark, I told PA plus PA dash is 1. So you can prove this theorem easily with the help of this approach. What is A and A dash? They are mutually exclusive. So probability of A union A dash is a omega and P of omega is 1. So P of omega equal to PA plus PA dash, and that's why it is 1. It can be proved trivially. Theorem number 2, if A is any event of omega, then probability of A always between 0 and 1. This is also proved by me under remark of classical definition. So what theorem number 2 says? For any event A of omega, its limit of probability is between 0 and 1. Theorem number 3, if A and B are two events of omega, such that A subset of B, then probability of A less than equal to probability of B. So what it says that chance of getting a smaller event is small than chance of getting a bigger event. A subset of B, that is A is a smaller, B is a bigger. So quite naturally you can say probability of smaller event is small than probability of bigger event. So these are the very simple theorems which can easily, trivially proved by exams.